All right, good evening to everybody. Welcome to this UCT Virtual Open Week. My name is Fred Nicholls. I'm currently the Head of Department of Electrical Engineering at UCT. And I'm going to tell you a little bit about the department, but mostly about electrical engineering, and I suppose why it's an interesting career choice and an interesting place to sort of take a career into. So I'm going to give about a 15-minute presentation talking about engineering in general, and then a little bit about the department and the programs that we offer. And then we'll do a question and answer session for probably another 10 or 15 minutes. There is a Q&A section that you can post questions to. And if we are able to, we will answer questions in that via text. And if we're not able to, then we'll pick them up verbally after the presentation. All right, so firstly, what do electrical engineers do? Well, ultimately, we try and make the world a better place. And to be more specific, we try and use our knowledge of mathematics and science or physics to make the world a better place. So engineering is basically the practical application of those particular disciplines. And our first and second year students spend most of their time doing a lot of maths and science, probably about 1,000 hours of maths and science in the first 2 years, because it is foundational and it's where the basis of engineering comes from. Right, so industrial revolutions. Engineers are revolutionary thinkers. They change the way that the world works. They produce things that change the way that things are done. And various examples are power systems, electrical systems, reticulation, water, sewage systems, transportation, either the devices that transport us or the networks that support those systems. Radio and radar, probably the most foundational electrical engineering disciplines. They're basically the start of electrical engineering. Telecommunications, big subject area nowadays, leading onto the internet. And sometimes it's quite hard to separate telecoms from internets. But they're riding on common types of technologies, and they both sort of deliver related services to the population. And finally, mechatronics, which is an emerging discipline, which is sort of a marriage between electrical engineering and mechanical engineering. And I'll have a little bit more to say about that later. All right, electrical engineering and the fourth industrial revolution. We have a lot of talk about 4IR. It's a bit of a catchphrase, and to some extent, nobody really knows what we're talking about when you talk about 4IR. But certainly there are a bunch of emerging disciplines and a bunch of emerging technologies that are really driving the field of engineering. And electrical engineers are very closely allied to many of these. So the first is machine learning and AI. You might say that's a computer science discipline, but electrical engineering is a very, very close friend of computer science. And in fact, electrical engineers can usually program, and they certainly need to be able to know what to program. So machine learning is a very big discipline there. Additive manufacturing, rapid prototyping, 3D printing, all of these technologies that allow you to actually produce little widgets basically from nothing at very low cost. They're changing the way we think about things. Previously, you would start with a big block of wood and carve away the pieces you didn't want to get left with something. But additive manufacturing is a completely different way of basically working with the process of production. Fifth generation wireless, 5G. It doesn't cause COVID, but it is a very interesting technology, or not technology, but sort of advancement of technology that creates wireless devices that are more useful for particular applications. So one of those applications, I guess, would be, for example, self-driving cars. In order to have intelligent transportation networks that know which devices or which vehicles are using them, we need to have very fast, low latency networks. 5G is one of the types of technologies that allows that to happen. Internet of Things, another sort of a catchphrase in some ways, but we are producing huge amounts of data, and you've got sensors everywhere. And one of the problems with the internet as it stands is the addressing mechanism. The IP4 network, I think, has only got 4 billion IP addresses, so separate addresses that can access or that can index devices. And I don't know, in my home, I've got at least 20 devices that attach to my local network. So we basically can't use internet technologies as they currently stand to extend to systems where there might be millions or even billions of devices attaching. So IoT is a drive towards having lots of tiny devices that are able to be networked and how to actually manage networks on that scale. I mentioned self-driving cars, autonomous vehicles. It's not just cars, it's also drones, it's also, well, I suppose aircraft and drones, and anything else that happens to be usually manually steered or manually controlled can be autonomously controlled using modern day technologies. Robotics is becoming a very big field, and again, it's not just having mechanical robots, but it's having robots that are also able to do intelligent things. So aligning robotics with machine learning is definitely one of the areas where we're pushing towards in the future. Nanotechnology and biotechnology, to some extent slightly related to one another, but other technologies, just yet further technologies that need electrical engineering disciplines and are currently very topical and very important for our short-term future. Right, so we offer 3 programs in the department, and they're just different flavors of electrical engineering. If you were to graduate with any one of them, we would expect you to be able to pretty much do any of the others as well. So the underlying qualification is electrical engineering, but one's banana flavored and one is cherry flavored, for example. So electrical engineering is the classical kind of thing when people think elec-eng, modern relevant engineering. So it's generation, transmission, utilization of electrical power. So basically ESCOM and technologies aligned to the types of things ESCOM does. And now, I guess the big push towards renewables. We're having 12 gigawatts of renewables being commissioned as we hopefully speak, which hopefully by 2023, I think we'll get rid of load shedding or something. One of the other areas in electrical engineering is machine design, and that's power electronics, motors, drives, battery charging technologies, and all the kinds of things that allow us to use electricity to move things and to actually generate, to do useful things for us. And again, that renewables would probably come into that in terms of wind farms. Optimizing motors and drives for wind farms is certainly a current area of interest. I think the little demonstration here, for example, this is the United States. I think this is in 2003, the Great Northwest Blackout, when 8 states and I think part of Canada lost the electricity power grid, basically due to a human error compounded by a whole lot of other unfortunate events. And it took 4 days, I think, to get the grid back up in that instance. We have a concern that if South Africa, if ESCOM loses the power grid, if it goes unstable and we have to shut it down, it could take weeks to get that thing back up again. It's an immensely complicated system and it's hard to control. Anyway, in terms of grids, there's a lot of cleverness coming into the grids, smart homes, I've mentioned renewables, consumer engagement, operation centers, distribution intelligence, plug-in electric vehicles. All of these kinds of concepts around elec-eng are becoming intelligent and becoming sort of computer aware. So they're no longer just systems that sit in the background. They're systems that we actively engage with in order to maximize the benefit to us and to maximize the efficiency of the systems. So classical electrical engineering people would be employed, for example, by ESCOM or in municipalities. Mines are huge users of electricity. Heavy industries, process industries, factories, Transnet, what's left of it. And that's basically sort of contemporary but classic electrical engineering. The second program that we offer is electrical and computer engineering. And this is for people that, I guess, can't really decide whether they want to do elec-eng or whether they want to do computer science, so they can do both. And it takes the best of computer science and electrical engineering and it sort of merges them together. And it involves the algorithms that run on the devices. It involves the applications that run on top of the algorithms to provide service level interaction, and also the hardware. That's one thing that the computer scientists don't do much of. We actually would build specialized hardware in order to maximize the benefit of particular applications. So here's some of the things that you might see. An embedded system is like a small computer, but it might be a very specialized or bespoke computer that has a particular application or a particular task. Very large-scale integration and processor design. If you think about a computer chip now, the level of complexity is so humongous that there's no way that you could design one without a computer. So we need to have very clever tools to be able to develop systems like that. FPGAs are reconfigurable computers. So they look like a computer on the outside, I guess, but inside it could reconfigure itself to look like any number of different computing architectures. And being able to program or specify a device like that is a very interesting problem. You basically need to write code that specifies the hardware before you write code that the software that runs on it. High-performance computer systems are a big part of electrical and computer engineering, and I mentioned reconfigurable computing. And then this whole digital signal processing is the algorithms that run on it in order to basically extract information out of data streams. Right, some people that are interested in that, the Square Kilometre Array is a huge project for building a massive radio telescope in the Southern Hemisphere. Graphics processing units, very good technologies that are being used a lot in machine learning, for example. I mentioned here telecoms, mobile phones, radar systems. Radar systems require very high performance electronic components, if you want to think of it that way. And things like banks and e-commerce, electrical engineers, they very often end up working either as management consultants or quite often just in the financial industries. The types of models that electrical engineers are good with are actually the same types of models that can be used to predict the stock market and to try and, I suppose, work on futures and derivatives. Telecoms, everyone probably has a telecommunications device in their hand. It's quite interesting to see the development of even just something like a cellular phone over the last 15 years. The changes are massive and they've been very fast in many respects. But it's not just the handsets that have become immensely intelligent, it's also the back-end technologies that drive them that has developed really quickly. So wireless telecommunications is a very interesting area with a lot of people working on it. Underneath wireless communications is how you actually transmit the data, or not necessarily underneath, it could be on top of, how you actually transmit data and how you encode the data, how you keep it secure, how you make sure that people aren't eavesdropping on it and things like that. Right, so I've been through two. Electrical engineering is our one program, electrical and computer engineering is our our second program, and our final program I mentioned earlier is mechatronics. It is an emerging field, and basically it takes the concepts of electrical engineering and marries them with mechanical systems and mechanical system development and design. And if that sounds like robotics, to a large extent, robotics definitely does fall into mechatronics. We also, in order to make an electrical and electromechanical system do something useful, we need to have a computer backend. We need to be able to control it and drive it. So we need control systems as well. And somewhere in the intersection of all of this is this field called mechatronics. The diagram, or the figure up here is a power line, and there's a power line inspection robot that runs along the power lines. It's actually this device over here. Runs along the power lines, busy inspecting that everything is in order, that the pylons are properly, that they have high integrity, that there aren't coronal discharges coming off the wires and things like that. That's a very nice mechatronics example. It's interesting. This is a low power, low voltage device running on power lines that might be 750,000 volts. And it's critical for us to inspect our power infrastructure. If I recall correctly, I think we've got about 30,000 kilometers of high tension lines in the country. And if any one of those goes wrong, we can basically lose our national grid, or at least sections of it. Here's an example of mechatronics. One of our staff is very interested in building bipedal robots, in other words, robots with legs, preferably 2 legs, so that they can walk like humans. But we're also interested in in thinking about how you can use biological systems to inspire or motivate the development of robotic systems. So what you saw there was cameras looking at a cheetah, markers on the cheetah being detected using vision systems and clever algorithms and all the rest, and being able to actually track that cheetah to work out the interesting things about how it articulates and how it moves and how it manages to do what it manages to do. Here is a robot that has a tail. Many animals have tails, and we've had people staff in our department doing work on what does a tail offer, and can a robot with a tail do things that robots without tails can't do? And the answer is quite definitely yes, they can. And down in the bottom right corner is one of the bipedal robots, Baleka, which has been developed at UCT and is able to be used as a test bed for these kinds of concepts. So none of these robots yet are intelligent to my mind, and they don't have vision systems attached to them. But as soon as you add a vision system to a robot, then you want to be able to give it the gift of sight, so to speak. And once it can see things, you also want to somehow give it ways of thinking about or reasoning about what it's seeing, and actually so it understands where it is and what it needs to do in order to achieve a task that might be required to be done. So giving robots intelligence is something that we're very interested in. Right, so that sort of leads to robotics, mechatronics, image processing. I've mentioned bio-inspired robots. We look at what nature did so that we can make robots better. You saw the power line inspection robots. Robot navigation and mapping. Robots need to know where they are so that they can do the jobs that they need to do. And in order to know where they are, they need to be able to build a map of an environment. So that's quite a big field in its own right. Prosthetics is an area. If you have clever prosthetics, hands, someone loses an arm and you put a prosthesis on them, you would like to be able to control it using brain interfaces, things like that. You don't want your devices to be cumbersome. You want them to actually integrate with the humans that are using them in those instances. And I've mentioned computer vision. Aerial robots, basically flying machines, are becoming very common. Everyone, not everyone, many people have a drone. Probably many people watching have a drone. And drones are able to do things now that they certainly couldn't do 5 years ago. And prior to 5 years ago, we didn't even have drones. And another area we're very interested in is marine robotics. There's a lot of imperative to have robots that are able to autonomously map the oceans or map the current algal blooms in the oceans. And in order to do that, we need robots that are able to navigate the oceans, know where they are, and be able to drive themselves to the places we need to get them to. Career paths, motor manufacturers. We've got a whole lot of medical X-ray companies in the Western Cape, for example, that are consumers of these kinds of people. South African National Space Agency, Anglo Platinum, De Beers, Amazon, Perilex, and so on. We've got a whole bunch of projects that have come out of UCT for improving the lives of people. Shack fires are a terrible disaster in this country. And Lumkani, for example, was an endeavor to produce devices that are able to warn people when shack fires are occurring and actually start saving lives in that regard. All right, so I've mentioned our 3-degree programs. All of them are accredited by the Engineering Council of South Africa, which means once you have a degree from UCT, you can travel internationally and use it elsewhere. I've said electrical engineering is our one program. It's our most general degree. It covers power and energy, and I guess to some extent electromagnetics. These sort of partitions are not 100% sort of in a box. Everything overlaps with everything else. Electrical and computer engineering, that's the discipline where we have specialized hardware and specialized software. Telecommunications and radar are 2 very good application areas that require both of those things in order to do what they need to be able to do. And mechatronics, electrical engineering for mechanical systems, and that involves production, control and automation, intelligent robots, and the like. One of the questions that I expect is going to come up, there will be people here that are uncertain about whether they want to do mechatronics or a degree from our mechanical engineering department called Mechatronics and Manufacturing Technology or something. And basically the difference, sorry, mechanical and mechatronic engineering, the MME program. They essentially, our program is electrical engineering with some mechanical engineering in it, but you would graduate as an electrical engineer. Their program is mechanical engineering with some electricals or electronics in it. So you would graduate with a mechanical engineering degree if you were to take MME. So I guess the gist is I've mentioned that all of these programs are just flavors. If you're uncertain about whether you want to do mechatronics or mechanical and mechatronic engineering, you should actually just not ask that question and ask yourself, would you rather do electrical engineering or mechanical engineering? And once you've made that choice, you make a choice between mechatronics or mechanical and mechatronic. The question is, are you more inspired by electrical engineering or by mechanical engineering? And then the question of which program or which department to do the program in, I think, answers itself. All right, thank you. I have completed the talk that I want to give. I'm unable to see from the interface whether there are any questions. Amir?
Hi, Fred.
Yes.
It's Naranya.
Hi,
There's a question regarding credits being transferred if someone has a diploma and they'd like to come over to UCT.
The answer to that is we transfer credits if and when we can. There are limits to how much we can transfer, but if you came from a national diploma or a BTech program, there probably are a few courses that we would be able to carry into our programs. I think there's a limit. There's a limit to how many credits you can carry in, but typically we don't come anywhere close to that. The problem with a BTech and an ND is largely got to do with a lack of mathematics and very often a lack of physics as well. So it doesn't normally save a year even, but it certainly does save having to do some of the courses. So it's unlikely that we'd be able to, for example, take somebody from a University of Technology background and completely exempt them from the first year. But we would be able to exempt them from certain subjects. And we would only know what those subjects are once we see what they've done and perhaps how well they've done in them. Anything further, Niran?
Not that I can see at the moment.
Super. Well, I think let's close it then. I'd like to thank, I don't even know if there's anyone in the room. I don't get to see from the other side. But if there is someone there, I thank you for being there. I've given an email address on this final web page, which is the email address of our undergraduate officer. If you do have any requests, you're welcome to contact her. Otherwise, if you have any other requests or other information that you need, feel free to contact the department. We do have a web page, which I'm sure you have access to and have knowledge of. And we will answer questions as they come. All right, I think that's it. Thank you all for coming and thank you for your attendance. And we look forward to seeing you at UCT. It's a very good university and we offer very good programs.